Hi everyone, welcome back to the channel. Let's solve a thermodynamics problem today. Most of the students have told me that they find it difficult to do problems like this, applying thermodynamics and also some of the mechanics involved in it. And so this problem covers a lot of ground. I'm going to solve this problem for two different cases, case 1 and case 2, and show you how to deal with such problems. And these kind of problems you see in every other examinations, and these are straightforward problem to some extent, but at least you need to know some of the basic things there and concepts. Okay, so let's get started and understand what is this problem all about. And I would also request you guys to just stick around and watch this video, and also try it out if you want to on your own. Pause the video and try it, and then come back and see the solution. Okay, so let's get into the problem. Find the work done by the piston of an air pump in order to pump a vessel of volume V from P1 to P2 by drawing air from it. If the change in volume corresponding to one stroke is delta V. So imagine a scenario where you would have seen there is a large tank with air and there is some pressure in the air which is greater than the pressure in the atmosphere. And then using a pump you take out some of the air and fill something else, like for example balloon, or also let's say the pressure in the cycle tire or like that. So if that kind of vessel is there and initially the pressure is P1 and using piston here we are pumping out the delta V volume, okay, and effectively finally we reduce this pressure to P2. Okay, so P2 is less than P1. So the question is, what is the work involved here? Now there is an undercurrent question also here that we need to understand or find out how many strokes. Okay, so when piston pumps out, let's say delta V volume, that's one stroke. Okay, so it has to do it multiple times. So how many strokes are required? Okay, so this is also an undercurrent question. We need to find this out first. And then let's look at the two cases. Okay, so case 1, assume that the air in the vessel is in good thermal contact with the surrounding. So what does this mean? It means that the temperature here, if let's say initially is T1, then this is going to remain constant. What we call is isothermal. Okay, so that's what it means when it says good thermal contact. There is no loss of temperature, is constant throughout the process. And case 2 is heat exchange is 0. So I'm sure you know about it. This is an adiabatic process. Okay, so I hope you see this properly. Okay, so let's start solving the problem for the case 1 first. Okay, I'm going to solve the case 1 here, okay, and case 2 here side by side so that you can compare what's changing in between. Okay, in isothermal means if you use PV equal to nRT, then T is constant. Okay, so which means that PV is also constant. So let's say that I'm using the pump trying to draw delta V volume, then at that instance, the overall volume of the tank increases by delta V because then this is going to push the air out. Okay, and the pressure will reduce, let's say, by delta P. Okay, so if initial pressure is P1V, then after one stroke, it will be P1 minus delta P, V plus delta V, isn't it? You get this? Okay. So P1 minus delta P is V by V plus delta V and P1. This is after one stroke, right? After one stroke. And I would encourage you to also see this using the other method because in some cases that method may come handy, which is if PV is constant, then if you take differential of PV, that will be 0, which is V dP plus P dV is 0, and therefore dP by P is minus dV by V. And if you integrate it from P1 to P1 minus delta P, and this one V to V plus delta V, then essentially you get ln P1 minus delta P by P1 equal to minus ln V plus delta V by V, right? And you can write P1 minus delta P is equal to P1 V by V plus delta V. So we get the same expression here too, but this might be handy in case where this is not so simple. There is an equation given for P and V, so you can't simply just use this one. You have to use the integration, okay? So just to show you how to deal with some of the complex scenarios as well. But I think we can deal with the current one, which is already complex enough. So if you see, this is after one stroke. Now, if you repeat the same expression for next pump, so it will be P1 minus 2 delta P V plus delta V, because the tank volume is always constant and the piston volume is also constant, or the pump volume. So equal to P1 minus delta P V, and P1 minus delta P is nothing but P V by V plus delta V, and therefore P1 minus 2 delta P is P1 V by V plus delta V whole square. So you see the pattern here. So let's say if it takes n strokes, so final P1 minus n delta P will be P1 V by V plus delta V n, and this is nothing but it's given that it has to be P2. Okay, so we figure out that n is ln P2 by P1 divided by ln V by V plus delta V. So that should be the number of strokes, right, to reduce the pressure from P1 to P2. Okay, so let's call this equation A. Okay, now the question is about computing the work done, right? So let's calculate what is the work done in single stroke, okay? And if we know that, then we can use that to compute the work done for n different strokes, okay? So let's call it dW stroke. And that should be equal to, let's say, sum prime dV prime V plus V plus delta V. So at any instance, if P prime is the pressure and V prime is the volume, this is how it is given, okay? Now in our case, we know that P1 V1 is P prime V prime. So P prime is nothing but P1 V by V prime, because V1 is V. So this will become P1 V, both are constant, dV by V prime, V to V plus delta V. Okay. Therefore, so let's call it single stroke is P1 V ln V plus delta V by V. So this is the work done by single stroke, right? Okay, so let's just mark it B. Okay. Now, how do we compute the work done for the entire n number of strokes? So let's see what is the work done by second stroke. Okay, let's call this W2. So this we can use the same equation, P1 minus delta P, because that's the pressure now, V, and same dV by V prime, right? And this is still going to be V to V plus delta V. And hence this will be nothing but P1 minus delta P V ln V plus delta V by V. We already know what is P1 minus delta P. If you see, we have computed here. P1 minus delta P is this, right? So we can use this and write P1 V by V plus delta V, right, into V ln V plus delta V by. And if you compute W3, it will be simply P1 V by V plus delta V square V ln V plus delta V by V. So total work done will be W1 plus W2 plus W1, right? And we know that this is something which is coming constant. So we can take this out. In all the expression, these are there. And then we are left with something which is V by V plus delta V. Okay. And if you sum this whole thing, let's say K equal to 0 to n minus 1. So you see why n minus 1? Because in the first case, this expression is not there, right? This is the first row. And from second it is appearing, and then it will go until n stroke. So it is n minus 1. This is nothing but geometric series, right? So P1V ln V plus delta V by V. And then what we will have here is 1 minus V by V plus delta V n 1 minus V by V plus delta V. Okay. And then if we simplify this, we will get P1 V ln V plus delta V by V. If you see, this is nothing but P2 by P1. We have already computed it. P2 by P1. And here it is simply delta V by V plus delta V. Therefore, you get P1 V plus delta V by delta V ln V plus delta V by V 1 minus P2 by P1. So that's the expression for the total work done. Okay, this is the expression for the total work done when the process is isothermal, right? Okay, so there are few key points here. So this is the work done. This was the work done for a single stroke, and these many strokes were required to reduce the pressure from P1 to P2. Okay, now let's solve the problem for the process when it is adiabatic. Adiabatic means that there is no loss of heat. Therefore, we can write PV gamma equal to constant. This is true for adiabatic process. And therefore, if initial pressure is P1, V gamma, then it will be P1 minus delta P, V plus delta V gamma. And P1 minus delta P is P1 V by V plus delta V gamma, right? So this is the pressure after one stroke. And by the way, you can still use the same concept which I covered earlier. So PV gamma is constant, which means dPV gamma is 0, which means P gamma V gamma minus 1 dV plus V gamma dP equal to 0. So dP by P will be dV by V gamma minus, right? And if we integrate it from P1 to P1 minus delta P and V to V plus delta V, which will give me ln P minus delta P by P minus gamma ln V plus delta V by V. Therefore, P1 minus delta P will be P1 V by V plus delta V gamma. Okay, so this equation is same as this. So we can still use this method as well. And this is going to be very handy when you get into some complex situations where P and V are not linear. Okay. So now let's compute the number of strokes here. So how do we compute number of strokes? So again, we can use P1 minus 2 delta P, right? V plus delta V gamma. That should be equal to P1 minus delta P V gamma. Therefore, P1 minus 2 delta P is P1 minus delta P V by V plus delta V gamma. And we already know that P1 minus delta P is P1, and hence V by V plus delta V 2 gamma, right? So eventually what we'll get is P1 minus N delta P equal to P1 V by V plus delta V N gamma, which is equal to P2. And hence in this case we'll get N equal to 1 by gamma ln P2 by P1 divided by ln V by V plus delta V. Now, if let's say we write this as A prime, so which one is greater? Let's in this, an adiabatic or an isothermal? So if gamma is more than 1, then an adiabatic is less than NA. So in this case, adiabatic case, we will require less number of strokes to get to the same pressure. Okay. So far so good. Now let's compute the work done. So again, we'll compute the work done for a single stroke, and that is again given by the same expression, P delta V, V to V plus delta V, except that here P1 V gamma is P prime V prime gamma. So this we can write as P1 V gamma dV prime by V prime gamma V2 V plus delta V. Again, if we integrate it, so first stroke we'll get P1 V gamma, and this one will be V prime 1 minus gamma by 1 minus gamma V2 V plus delta V. Okay, so we'll take this outside, 1 minus gamma, and this will be V plus delta V 1 minus gamma minus V 1 minus gamma. Okay, we just switch the sign from 1 minus gamma to gamma minus 1 so that it is positive, and then we'll just switch the sign here also. Okay, and what we get is one minus V by V plus delta V gamma minus 1 and into 1 by V gamma minus 1. So this and this will cancel out and only V will be left. So P1 V by gamma minus 1 . So this is the expression for, let's say, work done by single stroke first stroke. Okay, so let's write it like this. Okay, now we follow the same module and compute the work done 2 and 3 and all that. And I leave this as an exercise for you guys. Compute the work done for the second case and third case, and eventually you will get a geometric series. And again, if you sum all the work done by all the strokes, you will eventually get the work total as, I'm writing it because you can solve and you can come and match the answer here. Okay, so this is the answer, final answer for the total work done in case of the process is adiabatic. So I'm sure this has covered a lot of ground, would have given you a lot of insights into different aspects of thermodynamics and how to solve such problems. And Jay can ask any question here. It can simply ask how many strokes were needed, let's say in isothermal case or adiabatic case, or it can ask what is the pressure after m strokes and all that, or it could also ask, let's say, total work done. So I'm sure you would have learned how to solve such problems. Please like the video, subscribe to the channel, and share this with your friends. That's very important. Thank you very much. Thanks a lot for watching. Subscribe and gain access to concepts and tips for doing better in IIT, JEE, or other examinations. Keep up the great work.